Hello everyone, my name is Shikha Jain and now we move forward to lecture 4 of unit 2. So as I told you in the previous lecture about the deletion from the leaf node in a B tree, now we will talk about the deletion from a non-leaf node. In this case, successor key is copied at the place of the key to be deleted and then the successor is deleted. What is the successor key? That is the in-order successor. What is in-order successor? That is the next element in the in-order traversal, and the next element in the in-order traversal is the leftmost element of the right child, that is the successor. So in this case, successor key is copied at the place of the key to be deleted and then the successor is deleted. Successor is the right subtree will almost be in the leaf node. So let's suppose we need to delete 12. What is the successor 12? 15. So 12 would be replaced by 15 and we need to delete 12. Now this, we have replaced the values and we need to delete 12 here. So can we borrow from the left? No, we can borrow from the right. So 25 will go up and 20 will go down. So this would be the final scenario. 25 will go up and 20 will go down, and 27 and 28 here only, right? So let's suppose we want to delete 30 in this scenario. What is the successor of 30? 30 successor is 35. Right child, leftmost element. 30 successor is 35. 35 is replaced with 30. So now 30 is replaced. The 35 is here. Now here it is 30. We want to delete. Can it borrow from the left child? No, there is no left sibling of this particular node. Can it borrow from the right sibling? No, it cannot be borrowed from the right sibling because the minimum number of node would be 2. So it will be merged from the root node. So what is the final scenario? When we delete 30 from this tree, 35 would be here and 40 would be merged with this node. And all the left subtree would be same as that of the example. Right? So these are the scenarios we need to consider for the insertion in a B tree. Next comes B plus tree. What is B plus tree? A major disadvantage of B tree is inefficient sequential access. So there is an inefficient sequential access here. So if we want to display the data in ascending order of the keys, we can do an in-order traversal, but it is very time consuming. So when we want data in ascending order, that is very time consuming task in case of B tree. So there is a conversion of B plus tree. While doing in-order traversal, we have to go up and down the tree several times. The node have to be accessed several times in that case. We know that each node of B tree represents a disk block, and moving from one node to another means moving from one disk to another, which is very time consuming, because it is very time consuming from moving from one disk to another. So we need to check any other solution. So for efficient sequential access, the number of node access should be as few as possible. B plus tree is a variation of B tree and it is well suited for sequential access. So B plus tree is a variation of B tree and that is well suited for the sequential access. In B tree, all the nodes contain keys and their corresponding data items, records or pointers to records. There are records or pointers to records for containing the key value and child pointer. But in B plus tree, the structure of the leaf nodes and internal nodes are different. The structure is different in case of B plus tree, but in case of B tree, all the nodes contains keys and their corresponding data pointers of left and right subtree, pointers, child pointers, right? The internal node store only keys and child pointers, while the leaf node store keys and their corresponding data items. So internal node store only keys and child pointers, while the leaf node store keys and their corresponding data items. Data item are present only in the leaf node. In case of B plus tree, data item are only stored in the leaf node. The keys in the leaf nodes may also be present in the internal nodes. So keys in the leaf node may also have present in the internal nodes. In B plus tree, each leaf node has a pointer that points to the next leaf node, that is all leaf node forms a linked list. So all the leaf nodes in B plus tree forms a linked list so that sequential access can be easily formed. So this is an example of B tree: 30, 12, 20, 40, 50, 5, 10, 15, 19, etc. This is a B tree. And this is a B plus tree. So child node has a singly linked list type of orientation in this, and the root of this particular value is here, in this case 20. You can see 30 is here, 30 is here. So it is forms a singly linked list type, and sequential access is very easy in this case. In B plus tree, the internal node contain only keys and pointer to child nodes, while the leaf node contain keys, data items, and pointer to next leaf nodes. Right? The internal nodes are used as index for searching data, and so they are also called as index nodes. The internal nodes are used as index for searching data, and so they are also called as index nodes. So random and sequential access are simultaneously possible in B plus tree. So in B plus tree, random access as well as sequential access can be possible, and because the number of disk access would be more in case of B tree, it would be reduced in B plus tree, right? So B plus tree is the normal concept. Next topic is binomial heap. What is binomial heap? Binomial heap is a tree kind of a data structure. It is a collection of binomial tree. Binomial heap is nothing but a collection of binomial tree. What is a binomial tree? Binomial tree has some property associated with it. Binomial tree has some binomial coefficient, that is NC0, NC1 and NC2. What is this N? For number of nodes 2 raised to the power k. Let's suppose h is the height of the tree, then the number of nodes at any level, would be HCl. Let's suppose height of the tree is 2, and we need to find out at levels are 1. So 2c1 is 2 factorial by my 1 factorial by my 2 minus my 1 factorial, that is equivalent to 2, nothing but. So for one level, at one level the number of nodes would be 2 only. At third level, the height of the tree is 4, and the number of level is 3. So this will be 4 factorial by my 3 factorial, 4 minus my 3 is 1, that is nothing but 4. So we have at third level, we must have 3 nodes. At third level we must have 3 nodes. So HCl is the relationship which exists for the number of nodes at any level in binomial tree, not the binomial heap. So I have told you in this 2c0, 2c1 and 2c2. Accordingly we calculated the number of nodes at every level. So this is an example of binomial tree. So this is one scenario. You can see at third level what are the number of nodes. We can easily check. When the height is 3, accordingly height is also compared. Height of the tree is 3, 1, 2, 3, 0, 1, 2, 3. Height is 3. Height is what? Bottom to up. Level is what? Top to bottom. Height 0, height 1, height 2, height 3. Level 0, level 1, level 2, level 3. So for 3 height and third level, the number of nodes would be 1. How can we merge two binomial tree? Let's suppose we have this binomial tree, we have this binomial tree, we need to merge these binomial tree. So this or this, one would be a child of another, right? So we have placed this node here also. So the height would be increased by 1. In that case, the height would be increased by 1. So similarly, we have write H4, extra height binomial tree. One extra height binomial tree is created by adding two k minus 1 heights tree. That means H4 is built through H3 plus H3. H5 is built through 2 H4 plus H4. Right? So 2 into make k minus 1 trees would together contribute to one incremented height binomial tree. 2k minus 1 height tree would contribute towards the making of one more height binomial tree. So binomial heap follows the min heap property, and it is a collection of binomial tree. As you can see here in this example, that there is a linked list. It is a min heap, it is a min heap, it is a min heap. All the child are greater than the root node. All the childs are greater than the root node. So this is the binomial tree, this is the binomial tree, this is the binomial tree. This is the binomial tree of degree 0, degree 2, degree 3. Right? So the degrees are in ascending order. Let's suppose we have another binomial heap like this. Degree 0, degree 1 and degree 3. And we want to unite these two binomial heap. How can we unite these two binomial heap? We can simply unite these binomial tree by simply writing the same height binomial tree in similar fashion. 0 length, 1 degree, 2 degree and then 3 degree. So can we join these two? No, because the degree of this is 3 and degree of this is 2. We can join these two. Yes, we can join this. So after joining these two, we can start joining from the right hand direction. We can start joining from the right hand direction. So can we join these two? No. Can we join these two? No. Can we join these two? Yes. So when we join these two, so it will become one height. So 2 height binomial heap would be created like this. So after inserting these two height binomial tree, the sixth node, that is of 2 length, it can be joined with this because they both have degree 2. So after joining these degree 2 elements, we have degree 3, and that degree 3 is joined with the next level. You can remember here that in this case when we are joining, because when 7 and 4 is minimum, so 7 would be a child of 4. You can simply say that 7 would be a child of 4, right? So this is how the final binomial heap would be created, by uniting two binomial heap into one binomial heap. A binomial heap is a data structure similar to binary heap but also supporting the operation of merging two heaps quickly. So it can easily merge. They are mergeable heaps. The operations which we can perform in binomial heap are make heap, insert h comma x, find the minimum element, extract the minimum element, uniting two elements, and decrease key value. Assign to node x within heap h the new key value k, which is assumed to be no greater than current key value. So we can decrease key as well. We can change one value to another value using the decrease key function. Next topic is binomial heap extract minimum. So out of these, what is the minimum value? 1 is the minimum value. When we extract this one minimum value, we have these subtrees with us. So these subtrees would be we have subtree associated with it. We have extracted one from this. Now the linked list of x children is reversed and set head h dash to point to the head of the resulting list, that is another binomial heap. So all the elements of this would make another binomial heap with the head as h dash, and original have the head h. You can see here h dash have the child of this particular node, or we can say binomial tree, and h has the head as this. So we need to unite these two. So you know the procedure of how can we unite two binomial tree heap. So this heap and this heap can be easily merged through uniting binomial heap operation, right? So this would be the final answer by calling the binomial heap union operation to unite the two binomial heap h and h dash. So let's take a look at the algorithm of uniting two binomial heap. First is the binomial link y comma z. Parent of y is z. Sibling of y is child of z. So we are binomial linking takes place. Y, there is a y node, there is a z node. Parent, and we are linking the y and z. So parent of y is z. So z is the parent, y is the child. Sibling of y is child of z. Whatever the other child of z would be the sibling of y. Child of z is equivalent to y. Yes, this is the child of z. Degree of z is equivalent to degree of z plus 1. So we have incremented the degree to degree plus 1. And it will take O of 1 time. So let's take a look how binomial heap union operation occurs.